Yanofsky from CUNY speak to us in the experimental mathematics seminar, very appropriately, the shape of an experiment.
So first of all, thank you for inviting me and thank you for giving me a chance. Does this work?
Oh, sorry. It doesn't be plugged in.
Oh, okay. I'll just do page M. Okay. Okay. So here's the game plan. We're going to do some history, and then basically this is about no-go theorems, which you don't have to know what it is, but we're going to go through it. The most simplest no-go theorem is EPR, Einstein-Rosen. Then we're going to talk about, since we're talking about shapes, we're going to talk about simplicial sets, which is a combinatorial way of describing topological spaces. And then we're going to talk about empirical battles, some basic definitions using these things, and basic properties, and then actually go through 4 no-go theorems and do it. Okay. So, some history. So, these are just a list of some of the no-go theorems, and they started in 1935. Einstein, Podolsky, Rosen was the first one to say, look, something's weird about quantum mechanics. We got to figure out what it is. And basically their paper was a way of showing that quantum mechanics is not realistic in a technical sense of what it means. And so there's something wrong. In 1963-64, Bell showed that quantum mechanics is very weird and it's not local, in the sense that usually all of physics has been local, in the sense that something here happens, something there happens. It has to be close by for one thing to affect another thing. What he showed was it's not local. Now, there were other types of theorems that were related to Bell, called GHZ and Hardy, and which kind of showed the same thing, but in a niftier way. In the late 60s, there was Koch and Specker, and they showed, again, these are weird properties of quantum mechanics, that contextuality, namely, if you do an experiment, the outcome of an experiment depends on the context of what the experiment is. Okay, so if you ask a question in a certain way, you'll get one answer. If you ask a question in another way, you get another answer. And it's very, it's not something, it's true. I mean, it's a real theorem. Okay, Conway-Cochin was something that came out in 2006 that said, even non-contextuality, it's very strange. Okay, I'm not going to get into that. Okay, now, after all these, so different researchers, Dixon, Fine, Jarrett, Perez, Redhead, Shimoni, etc., all these things, they went through and they described all these different properties that quantum mechanics fails. Okay? These no-go theorems that show that quantum mechanics fails different properties, they went through them and they showed which ones they satisfied, which ones they don't. And they did very, they explained it very nicely. However, they did it in many different ways, in many different languages, and in different things, and various properties of quantum mechanics. Now, okay. 3 years ago, me and Professor Adam Brandenberger from NYU wrote a paper called The Classification of Hidden Variable Properties. Okay? And what we did was we gave a unified presentation of all these different properties. It's one presentation that describes all these different properties in one way. And the unified presentation is basically probability theory. Basically, given a certain measurement, what's the probability of getting that outcome of the measurement? And it's a classical probability theory. It's a very simple, it's easy to read paper. I mean, it's basically 11th grade, they teach now conditional probability, so any 11th grader can read this paper, and it's very readable. Okay? But we did one thing further. We describe all these probabilities, all these different properties using probability theory, and then we put them into a nice Venn diagram, which again organizes them, what implies what. Weak determinism implies outcome independence. Whatever these properties are, and we'll talk about it later on, but we get these different properties, and you have 6 different properties and I think 16 different regions describing what these properties are. And again, it's all done with probability theory. So certain probability distributions can occur or cannot occur. And then we go one step further, and we say, what regions can happen and what regions cannot happen. Okay? So this region can happen. So you can have a probability distribution that does satisfy weak determinism. Okay? this says you can have a probability distribution that satisfies outcome independence and parameter independence. Whatever those mean. We'll see later what they mean. So we have all these different regions, and we show when they can happen, when they can't happen. Now, the purpose of the no-go theorems, EPR and Bell, and something over here called no signaling, the purpose of those no-go theorems is say, you know what, you cannot have quantum systems satisfying these properties. In other words, EPR says you will not have a quantum, there is a quantum system which is single valued and weakly deterministic, and just weakly deterministic, and it fails. Okay? So again, the purpose of the no-go theorem is to show which properties can happen and which properties cannot happen. Okay. Anyway, so we did this paper, and it's a beautiful paper. And again, it only uses the language of classical probability theory. Okay, no physics whatsoever. As mathematicians, you all appreciate that. No physics whatsoever. All statements about probability theory. So it's a very nice thing. However, we cheated. We look at what the physicists do, and we did, and then we got from them those examples, and we showed. However, the statements are all statements of classical probability theory, and not even complicated things. No Bayesian analysis or anything like that. Okay. Then Samson Abramsky went further with this. Okay, and he said, let's look at relational hidden. He wrote a paper called "Relational Hidden Variables and Non-Locality," and rather than looking at probability, he said, look at a relation, which is a subset of outcomes cross measurements. Okay? And basically, an outcome is related to a measurement if and only if the probability of the measurement, the probability of an outcome given a certain measurement is greater than 0. In other words, if it's not a 0 thing, then these two things are related. And what he did was he got much of the previous work done by simply looking at this relation. So he went, I guess conditional probability is taught in 11th grade. In 10th grade, you can teach about relations. And so he did, his paper went on much further and did much more interesting things. But much of the same things that we had before, he did with just talking about a relation. And it's very nice. Okay, that's fine.
It was based on your paper?
He had our paper, yes, it was based on our paper, but it took it further.
Yeah.
Okay. Some things else. There is a need for a clear discussion of compatibility of measurements and its relationship with locality. Okay, now there's two strange things about quantum mechanics. One is the Heisenberg's uncertainty principle, which says basically that it could be you could have two measurements and you're going to get two different answers if you do x first and then measure y, or if you measure y first and then you measure x. Okay? So the question is, some measurements are compatible, some measurements are not compatible. Okay? That's one strange thing about it. And the other, there are a few very strange things about quantum mechanics, but that's one major one. And the other one is locality, that things far apart, things that are far apart can still affect each other. Okay? And that's, now, so that was somewhat missing in the previous work, and so that needed to be done. Okay, Abramsky and Brandenburger got together, and they wrote a paper called A Unified Chief Theoretic Account of Locality and Contextuality. Contextuality is another way, is a way of talking about compatibility. And they discussed this topic very well, and they got some nice results. Okay, so this is kind of a previous, this is what I'm working from, and now I want to show you what I'm doing. Okay. We went from probability to relation, and now I want to do something even simpler, namely a function. Okay? It can be looked at as a special type of relation. A special type of relation, a function is a special type of relation. Okay? So a function from outcomes to measurements. So rather than looking at the set of outcomes and looking at the set of measurements, we look at them, a function from outcomes to measurements. Okay, now let's look at the set of outcomes. The set of outcomes has a structure of a space. Okay, it's not just one outcome happens here and one outcome happens there. There is whether or not two outcomes are related to each other, whether or not two outcomes can occur at the same time, can co-occur. In contrast, the space of measurements, that's where the weird thing happens about Heisenberg's uncertainty principle, that compatibility. The set of measurements has the structure of a space also. Okay? And so we're interested in this map from outcomes to measurements, but each one has a certain space. And we're going to see the relationship between these two things. Okay. The map from the outcomes to measurements preserves the space structure. So we want some map from O, outcomes, to M, measurements. E stands for experiment, and it should preserve that structure. I'm going to show you what type of structure I want. Okay, outcomes of this map are, okay, now here's the thing. You have a measurement, you have a Geiger counter, you have a thing to check spin, a Stern-Gerlach experiment to check spin. Those are measurements, okay? Then you have possible outcomes of the measurements. What's the possible outcomes? The Geiger counter beeps, the Geiger counter doesn't beep. It's spinning up, it's spinning down. Those are the outcomes of the measurements, okay? The spectrum is this way or the spectrum is that way. These are the types of outcomes that you can have of these things. Okay, outcomes of these maps are kinda, not really, I'll show you what I mean in a minute. They're right inverses of this map. So again, what basically you have is this map from outcomes. What's the possible outcomes to the space of measurements? So here's your Geiger counter, and you have the Geiger counter beeped, the Geiger counter didn't beep. Here's your Stern-Gerlach thing where you do checking spin. It spins up, it spins down. Okay, and so you have a map from spinning up, spinning down, down to the spin checker. And here you have beeping yes, beeping no, down to your Geiger counter. That's the way to think of it. Now, what's an inverse map to this, a right inverse? That takes a measurement and gives you an outcome. Okay? That says, oh, that's the results of an experiment. If I turn the Geiger counter on, does it beep or does it not beep? Okay? If I turn the spin checker, does it spin up or does it spin down? So this is kind of the setup of the experiment, and the inverses to this map, the right inverses, and I'll show you why it's right inverse in a second, is kind of the outcome. It's kind of the results of the experiment. Okay, so you have an experiment from here to there, and the results are the type of right arguments, the right inverses that you're allowed to have. Okay. No-go theorems are about certain systems that cannot have certain properties. So what we're going to talk about is the type of right inverses you can and cannot have. Okay. I got a little abstract, so let's go down and do a real experiment, a real thing. So EPR, 1935, Einstein, Podolsky, Rosen, and what they talked about, well, they didn't really talk about spin, they talked about something else, but Bohm later on fixed it up, and he talked about spin. Okay? And basically, a particle can spin this way or a particle can spin that way. Okay? Don't want to get into it. By the way, if you can do this. Okay, so here's the classical thing. You have Anne and Bob, okay? And they're each doing an experiment. And they're compatible. Namely, there's no Heisenberg uncertainty principle here. Whatever Anne does, Anne can do and Bob can do, and there's no problem whatsoever. Work? Yes. Okay. Okay. Now, again, what you're doing is you send Anne a particle and you send Bob a particle. And you're measuring spin. Rather than saying things like spin up and spin down, we're going to say red and green. Okay? Throughout the rest of the thing, we're going to talk about red and green. So what possible things can happen? Well, Anne can measure red, Anne can measure green. Bob can measure red, Bob can measure green. I press the button on the side?
The front, the left and right.
Ah, okay. And this is the possible things that can happen. Okay? Now there's 4 possibilities here. Again, they can both measure red, they can both measure green, Anne can measure red, Bob can measure green, or this way. Now, the way to think of this is these are the possible outcomes, and they're mapping onto this measurement. And the interesting thing is, the right inverses of this map take this, and there are 4 possible right inverses of this map, because there are 4 possible things. Okay, so that's a nice experiment with 2 particles and 2 different people measuring them. Okay. Now, what entanglement is about, what this non-locality is about, is as follows. Let's say you have a particle that has no spin. You have a particle that has no spin. And you split this particle into 2 particles that do have spin, whatever spin is. Okay. Now, there's a law of the universe. It's called conservation of spin. Okay. It is a fact of the universe. So, if this one's going to be spinning counterclockwise, then this one's going to be spinning clockwise. If this one's going to spin this way, then this one's going to be spinning this way. Okay? That's what entanglement's all about. The shocking thing is, this particle can be across the universe, and this particle can be across the universe, Okay? And if you measure this one, that one automatically collapses. Okay? Just to preserve conservation of spin. Okay? Just like we have conservation of momentum, conservation of energy, conservation of this, conservation of that, you also have conservation of spin. Okay? Okay, so let's see what happens. Oh, by the way, so this is what's going to happen. You have your particle in here with no spin, and you split it up into two parts, and here you have a way of measuring it. You might think that this is and if it spins this way, it's red, and if it spins this way, it's green. And Bob has, if it spins this way, it's red, and if it spins green, it's green. One thing for sure that we see, okay, here's what we have. We have Ann and Bob, just like before. Okay, but this time, it's not I send him one particle and him one particle. They both come from a spin with, from a particle with no spin, and I split that particle in two, send it one to him, one to her. Okay, and then what we have is, Ann can have red and green, Bob can have red and green. But now, if Ann is red, Bob is automatically green. And if Ann is green, Bob is automatically red. Okay, so that's a restriction on the space. This is not as big as this space, it's like this. Okay, and this is a statement of EPR. Not in their language, but that's fine. There exists an empirical model, that's an experiment, okay? Leave me space, I need to write something there, which does not satisfy outcome independence. Now I've got to tell you what the property outcome independence is. Outcome independence means given any two possible outcomes, they can occur. In other words, one outcome is independent of the other outcome. So if this one's red and this one's green, that has that. That has that. Now, here we have it very nicely. This satisfies outcome independence. If Ann is red and Bob is green, there's a line in between them. If Ann is red and Bob is red, there's a line in between them. This does not have outcome independence. Okay? Okay? You cannot always lift this thing up to anything here. Okay? And so that's a fancy way of saying that you have some type of restriction. So it does not have what's called outcome independence. Okay? Questions? No? Okay. Okay. Now, we're going to come back to this in a second, but we have to talk about some hidden variables. Okay? One of the reasons why Einstein wanted this was he wanted to talk about hidden variables. His purpose was saying, you know, quantum mechanics is incomplete. He says, you need something to talk about. There has to be some other things going on. Okay? And his thing was that there might be hidden variables. Hidden variables are, it's like something in statistical mechanics. You don't know exactly what's going on, but there must be something else out there that's explaining it. Okay? Okay. In terms of maps, so what hidden variable does is it ensures some types of determinism. One of the things in quantum mechanics is things are non-deterministic. You do an experiment, you do the experiment, you get one possible answer. You do the exact same experiment, you get another possible answer. Okay? Why should that be? Why should it be that if you do one experiment, you can get two possible answers? In every other branch of physics, okay, there is determinism, and yet quantum mechanics doesn't have it. So Einstein was pushing that maybe there is some deterministic way of doing it. In terms of maps, this is making the map from O to M into an isomorphism. What do I mean by an isomorphism? I want, right now this is an onto map. From here to here is onto, it's not into. I want isomorphism, namely, you give me a measurement, I'm going to tell you exactly what the outcome is. One possible outcome per measurement. Okay? That would make this into an isomorphism. You want this in an isomorphism. Rather than look at the map at O to M, look at a space lambda, that's going to be your space of hidden variables, and a function O to M cross lambda. In other words, it's not just the measurement. It's not whether or not this measurement, this Geiger counter is going to beep or not beep, but there's some hidden variable, there's some other thing going on here that's going to explain whether it's going to beep or not beep. So when I'm looking here at a Geiger counter, it's not just the Geiger counter, but there's something else affecting it. Okay, and given a measurement and the hidden variables, there will be exactly one outcome. And that's what we're trying to do in terms of determinism. So we're trying to beef up the space of measurements by adding in the thing. Okay, in a sense, the lambda is the kernel of the experiment. This is for group theories. In a sense, lambda is the kernel of the experiment map E. In group theory, if K is the kernel of O to M, then O to M cross lambda, not really cross, it's tensor power, whatever, is an isomorphism. Okay? So again, how far you are from being deterministic is kind of the kernel of this map. Okay. For EPR, we have a hidden variable space, lambda and lambda prime. You need a hidden variable space with two things, namely to tell you what two things to do. Okay? We're not going to do this, so whatever. So here you have a map, here you have an outcome to space of measurements.
So this is your way of presenting EPR, right?
Yeah.
Not how Einstein.
No, it's not how Einstein had it. It's a very readable paper, and it's also the most quoted of Einstein's papers, is his 1935 EPR. And you have, okay, let's forget about that. H is equivalent. I get flogged if I go beyond 45 minutes. Okay, so let's go back to this thing. So this was the unentangled. Just send two particles this way and this way. This is the entangled. And now let's talk about hidden variables. So now you have Anne, but Anne is with lambda. And Bob is with lambda. This is fine. But what I just showed was you need two lambdas, a lambda and a lambda prime. Okay, and a lambda prime here, and they should be compatible. Now notice, this map is now an isomorphism. Okay? Either this goes here, or this goes here, whatever, but it's an isomorphism, which is exactly what we need. Okay? So we beefed up the space of measurements so that there's an isomorphism, so that this map is an isomorphism. Okay, theorem, EPR. This is, again, not the way he's mentioned it. There exists an empirical model for which there is no equivalent hidden variable model. In other words, if you're talking about hidden variables, that satisfies single valueness. In other words, you need more than one lambda. Otherwise, this works. In a sense, this has one lambda, and that didn't work. It wasn't. Also, it's outcome independence. Not only is it deterministic, but it's outcome independent. Okay. So fine, so this is what I'm trying to do. This is for a baby example EPR, but what I'm trying to do is set up the space of outcomes, the space of measurements, talk about them and talk about the functions in between them. Okay, so the space, I want to talk about space, topological space, but what I'm using is the combinatorial description of topological spaces, which is simplicial sets. Okay, simplicial sets. So let's talk about what they are. They're a generalization of simplicial complexes, which is still taught in first year topology courses. Okay? And simplicial complexes are nice spaces constructed by gluing together points, line segments, triangles, and simplices. Okay? And this is a typical example of a simplicial space. Okay? And nice topological spaces are homotopy equivalent, whatever, to simplicial complexes. Now let's abstract that a little, without mentioning the word category theory. A simplicial set is a bunch of sets. It's a sequence of sets. Okay? And x0 is going to correspond to the 0 cells. x1 is going to correspond to the 1 cells. x2 is going to correspond to the 2 cells, the triangles, etc. It's a sequence of sets where xn is the set of n simplices. Okay? Again, triangles, lines, etc., etc. Okay, but it's not only that. Set of n simplices together with face intergeneracies functions. Okay? So you're going to have maps from xn to xn minus 1. I'll show you what they do. You have maps from xn to xn plus 1. Okay? And this is the way to think of it. This is the picture of it. You have points, you have lines.